Before we leave this chapter, I wanted to show you the generalization of Taylor series for functions of n variables. I think it's pretty cool. I've been saying all along that the gradient vector is the multidimensional analog of the first derivative, and the Hessian matrix is the multidimensional analog of the second derivative. And I think this is a really great way to see what I mean by that. So just to jog your memory, at the end of Calculus 2 you learned about Taylor series. If I have a function f and I can take all of its derivatives at x equals a, then often we can approximate f with a truncated Taylor series. As long as I'm close to a, usually this is a decent approximation of this function. And provided this isn't some strange piecewise function or something like that, most of the time this is true. Yeah, so if f is infinitely differentiable, so I can find f of a, f prime of a, f double prime of a, f triple prime of a, and the remainder goes to 0 as n goes to infinity, f of x will converge to its Taylor series centered at a. And remember what we said in Calculus 2, if we have a function and it looks like this, let's say that this is x equals a, well, the 0th degree Taylor polynomial, that's just the function value at a. So it's actually a pretty lousy approximation. It's just f of a. And the first degree Taylor polynomial is f of a plus f prime times x minus a. And that's really just the tangent line there. So I would sketch the tangent line. And the second degree Taylor polynomial, that's f of a plus f prime at a times x minus a plus 1 over 2 factorial, which is 1/2, times the second derivative at a times x minus a squared. That's going to be a best fit parabola. It will have the same function value, it will have the same first derivative at x equals a, and it will also have the same second derivative as the function does at x equals a. Maybe it looks like this. So that's t sub 0, that's t sub 1 of x, and that's t sub 2 of x. And we can keep going like this. All of these polynomials will agree with the function up to the nth derivative. So if this is t sub n of x, the function value at a, the first derivative of this at a, the second derivative at a, all the way up to the nth derivative at a, all of those are going to be correct. They're going to be the same as the nth derivative of the function at a. And then we're just going to draw a polynomial and we're going to see, wow, that's a really good approximation. Well, the same thing is true with functions of several variables. Now we need new notation if we're going to do this with functions of several variables. So I might have a function f of x, or z equals f of xy. Now in order to represent this in a notation that looks similar to this, we're going to change this xy to a vector. So I'm going to call this f of x, the vector, where x is a vector with components x and y. And instead of a, I'm going to use the vector x naught, and that will have components x naught and y naught in it. So it turns out that this function f of x can be expanded in something that looks like this, provided I change my notation just a little bit. Now, the gradient of f at xy, that's still the partial, or the vector of first partials. The notation that they're using here is these parentheses. I know we're using them differently. And we would evaluate, up here we're going to evaluate the gradient at x naught, y naught, but we'll do that in a little bit. So they're using parentheses here. Actually, there shouldn't even be a comma there. So that is a row vector. These are column vectors. And our second derivative, the analog of the second derivative is the Hessian matrix. And that's that matrix of second partials. Well, one other thing that we need to know before we write down something that looks like this. If you have a column vector, like this vector xy, and you want it to be a row vector, you want to just change this column into a row, you write it this way, and that little t means transpose. So this is red x transpose. And that just means you take all of the columns that were formerly columns and you make them into rows, and all the rows and you make them into columns. So you just sort of switch everything. So x transpose, if that's our vector x, is a row vector now with components x and y. So we can put all these pieces together and we can come up with something that's like a Taylor series for our function f of x, y. We're just using this new notation. So f of x can be expanded in this Taylor form. So we'll have f at x naught plus something. Now, in order to understand how this next term works, you have to remember how matrix multiplication works. If you have a matrix A and a matrix B, you can only multiply them if the dimensions are just right. So let's say matrix A is an n by m matrix. This is the number of rows of A, and this is the number of columns of A. So I've got 1, 2, 3, that's n rows, 3 rows, and m columns, 1, 2, 3, maybe 4. That's the number of columns. So it's m columns. Now in order to multiply these guys, the number of columns of the first matrix has to equal the number of rows of the second one. These two have to match. And that doesn't necessarily have to be the same as that one. That could be p. And the product, AB, will have dimension n by p. Now remember, f of x is a real valued function, just like it was over here. So this is giving me a single real number. Or I could think of that as a 1 by 1 matrix if I want to. So when I expand this, I can't just take this derivative evaluated at a, which is a number, and then multiply it by this other number, x minus a, or this expression that represents a number, x minus a. I've got to multiply in just the right way so that the analog of the derivative, which is the gradient, times this vector x over here makes sense. Well, if I do this, let me see. I want to make sure, I'm going to be 100% sure that I'm doing this correctly. Yeah. If we do this, take the gradient and evaluate it at x naught, and then multiply by the vector x minus x naught. I believe that has the right size. Let's check. So this is a vector with components, partial of f with respect to x at x naught, partial of f with respect to y at x naught, and this is a vector with components x minus x naught and y minus y naught. So I've got a row vector, so it's one row by 2 columns, and then I've got a column vector, it's 2 rows and 1 column. So these match, and then when we're done, we're going to have a 1 by 1, which is exactly what we want because that's just a real number. That's a 1 by 1. So f can be expanded in this way, and I know it doesn't look like it, but this is actually an alternate form for the tangent plane. You're thinking to yourself, what? I know. Like over here, our first degree Taylor polynomial was the tangent line. Over here, when we write this in this form, we've got the tangent plane. Blew my mind the first time I realized it. So this is the tangent plane, and then you'd say, okay, well, what does that mean? So here's our surface. Maybe that's our point x naught, y naught, and the corresponding z value, z naught. So it's given by f of x naught, y naught, which is f of the vector x naught now. That tangent plane right there is given by this formula. If I expand it, it's going to be the same tangent plane that we've studied previously. And you say, okay, well, how does that change? How do we add this second order term? Well, we have to be careful about this because of the way matrix multiplication works. So we've got this, and we're going to add 1/2 still times the following. It's going to be this x minus x naught, but instead of being a column vector, it's going to be a row vector. So it's x minus x naught transpose times the matrix of second partials evaluated at x naught times x minus x naught. So this is acting like the first derivative, so it's like the first derivative times x minus a. And here we have 1/2 times the second derivative times x minus a squared, but it's a little bit funny looking because of the way matrix multiplication works. But let's expand this just to make sure that we're clear on why this is true. This is x minus x naught, y minus y naught. It's a row vector. It's one row by two columns. This is the matrix of second partials. Evaluated at the vector x naught. And then and that's a 2 by 2. And we're taking that and we're multiplying by this column vector over here with components x minus x naught and y minus y naught. It's 2 rows by 1 column. So those match and those match, so we should be able to multiply them. And when we're done, the result is a 1 by 1, and we're going to multiply it by 1/2. So if you're saying to yourself, like, what does that mean? Well, if I put all of these pieces together, basically what we're going to get is the best fit elliptic paraboloid right there. This one looks like it's kind of concave down, or like in multiple directions. So on the other side of this, I would see like an elliptic paraboloid that like fits over here. Maybe it looks like this. That's a really ugly elliptic paraboloid, something like that. And it fits against the surface and it passes through that point. So this looks really bad, but let me write it out one more time, a little bit cleaner. So here's our Taylor series. F of x under certain conditions can equal f of x naught plus f prime at x naught times x minus x naught plus 1/2 times the second derivative at x naught times x minus x naught squared, oops, x naught not a, and so on. And this is going to give us basically a best fit parabola that fits our curve. It has the same function value, first derivative and second derivative as our curve. And then under certain circumstances, the function f can be written this way: f at the vector x naught plus the gradient at x naught times the vector x minus x naught. Here, instead of this, we've got to do something sort of different. We've got the x minus x naught transpose on this side, the Hessian evaluated at x naught, x minus x naught just normal on the other side. And when I put all of these pieces together, I get a best fit elliptic paraboloid. So this elliptic paraboloid has the same function value at x equals x naught. It has the same gradient at x equals x naught as the original surface, and it also has the same Hessian. It has the same matrix of second partials as the original surface. And we could go further. We could find another polynomial function in x and y that would fit the surface by taking another term after that and another term after that. I just thought it was cool. You won't be tested over this. I just wanted you to see that all of this applies to higher dimensions. Now, I wrote all of this as if we were dealing with a function that depended on two variables, x and y. But if you look at everything down here, notice that there is no indication of what the dimensionality of any of this is. X naught could be a vector with n variables in it. Then this would be a matrix, a row vector with n components. And if this has n components, then x minus x naught will have n components. And then this would be a 1 by n times an n by 1. So actually everything that I've written here works when x is a vector with components x sub 1, x sub 2, all the way through x sub n. So we don't even need functions of two variables anymore. We can use functions, we'll have functions of n variables, and we can expand them in this way. Now, in order for this picture to make sense, we need to have functions of two variables. We're not actually going to be able to see anything when we've got functions of three variables or more. But with a function of two variables, we have a surface, and we've got a tangent plane and an elliptic paraboloid that fits the surface at that point. And when I say fits, what I mean is it has the same function value, it has the same gradient, and it has the same matrix of second partials at that point as the original surface does.